You can tether off your phone. We don't use a lot of data, so it's not like watching YouTube or something like that. But if you don't have any of those available to you, then I'll step through the lab for us today. Okay, I'll skip all the reading and let you do that as well. By the way, up in the upper left corner where it says File, you can actually download the whole notebook as an IPyND. So if you want to have this, or you can download it as a PDF or whatever you want, but if you want to have this lab available to kind of read through again, if you like, basically you can reproduce this entire lab on your own pretty easily. We've talked about all the software in this notebook. We've talked about all the software that we use. And so you can actually do this lab on your own as well. But for those of you that are stuck on the Stanford guest and actually can't get through, I want to kind of walk you through this a little bit. I'm going to skip this reading. Okay, it essentially is probably a more elegant description of what I was trying to say earlier about what are GANs, why are they used, how are they used, and so forth. So I'm going to go through the steps that require digits, because those are the ones that are difficult. So you'll see here it says on the digits homepage, you can select the dataset tab to view all existing datasets. Again, digits is a tool written by NVIDIA, provided by NVIDIA, for people who want to do data science. It's intended to be very easy or simple on-ramp to using GPU deep learning frameworks. And so it's trying to take out some of the complexity. Okay, you can download TensorFlow or you can download Caffe or any of those things, but some of them require a bit of work to get set up and get running and get your data imported properly. And that's where we feel that digits could be a help for those who are getting started, need a real easy way to start doing deep learning with GPUs. So you'll see it's kind of nice, it's kind of minimal, nice GUI. We're not going to be typing any commands from command lines or things like that. We're just going to be doing mostly point and click, fill in some fields and so forth. So from our notebook, the first thing it says is select the MNIST classification to look at the data. So we've already imported the data, all right? And I can explore the database. In other words, what images are in the database? And now you can kind of see here that it's showing me all images, or I can filter by class. Essentially, I'm just looking through the database of images. So we had a bunch of these images. They were PNG or JPEG or something like that. We import them into digits, which is importing them or putting them into an LMDB database. And that has sorted all of them by class. And you can see I can scroll around and look at these digits. Right, so if you look at the variety of sevens, for instance, some of them are just kind of plain. Some of them have the cross on them. Some of them are a little bit squiggly. And so we're looking at many, many different types of sevens. But all of us in this room would easily identify most of these as the number 7, right? We want our computer system to be able to do the same thing. Okay, so we have just explored the data set. Okay, so the next thing we're going to do, I'm not going to look at the network topology, but you can certainly do that. I'm not going to talk about the objective function either, but it's an important piece of it. The next thing we want to do is look at training a model. Okay, so we want to train a model. We want to train a generative model. Okay, and so what we're going to do is, based on these directions, we're going to select the MNIST generic data set. All right, so I'm going to go back to the digits main page. I'm in the models tab. New, other, and the username doesn't matter. It's just to identify you versus somebody else who might be using digits at the same time. So when you train a new model, there are some settings that you're going to change. These are all listed in the notebook. I just have them memorized because I've done this many times in the past week. Changing a few things now. It looks like I'm just changing these things arbitrarily, but I'm actually changing them according to the instructions. Okay, changing the learning rate a little bit. The next thing we're going to do is actually put in a custom network. Okay, and it's going to be a TensorFlow network, and if you look, I need to copy paste this network definition. So what digits allows you to do is either use 3 predefined networks, LaNet, AlexNet, or GoogleNet, or you can create your own network. And as you can see here, you can use either Caffe, Torch, or TensorFlow. Okay? Now I can actually visualize the network, but I'm not going to do that right now. This is my network. Now I'm going to rename this and get this started. I think it says to rename it. So basically what I've told digits to do now when I click create is to run the training. Okay, now this is the thing that's going to take a few minutes, but this is actually running the training. Setting up on the GPU, I've got the data, and I've told it what to do for the training. I've said run 5 epochs, that's 5 full cycles through all the data. And you can see we're running a Tesla K80 right here. TensorFlow allocates almost all the memory on the GPU, unless you tell it not to. That doesn't mean it actually uses all the memory on the GPU, but it just allocates the whole thing and then kind of has its own memory pool, uses it like a memory pool. Okay, so now you can see we're actually running, okay, the process, memory, and CPU, and GPU. Wow, this is hot already. 84 degrees Celsius. Wonder which data center this is. It's warm, right? 54% GPU utilization. That's just a measure of how much the GPU is being used, the compute portions of the GPU. The memory being used, these are K80 GPUs, so they're a Kepler generation. So 2 generations prior to our newest ones, we have Volta now. Prior to that, we had Pascal, and prior to that, we have Kepler. But you can see what's happening. This graph is changing as the training proceeds, right? And the idea, especially with digits, is that you can see graphically what's going on. And that way, if you don't like how your training is proceeding, then you can stop and change things and restart. Right? Some of these jobs take days, if not weeks, some of the big jobs. Right? And we don't want to run a training job for 2 weeks and then find out that the job didn't proceed properly, okay? So the idea here is we can have a graphical view of what's going on, and you can see that on the bottom is the key. So all of the accuracies, there aren't any. Maybe I gotta scroll down a little bit here. You can see the graph has, you can mouse over the points, and you can see the values there. And what we want is actually the generator loss and the discriminator loss, so these 2 lines, to be very similar to each other, right? If they diverged, that would mean that one of them was doing much better than the other, right? We want them to be adversaries, but in order to have success, we want it to be a situation where the generator and the discriminator are roughly the same in terms of loss, because if they're exactly the same or roughly the same, that means that the generator is doing as good of a job as it can to fool the discriminator, and that means that the discriminator is getting the answer right about 50% of the time, right? So that's really the idea. It's getting the answer as well as it can. So you can see we're now on the bottom. We told it to do 5 epochs. It's right at 1.2. So this is the part where if you're actually able to get connected, you can be running training. So because we're using TensorFlow, we can also add hooks to display some of the images that we are generating. Okay, so I can actually open TensorBoard, which is TensorFlow's visualization tool that they provide for looking at what's going on during the training sequence. This tool is an extremely good tool. It's so good that actually Microsoft, their version of machine learning tool called CNTK, they actually have hooks built into CNTK to use TensorBoard. Okay, so they thought, well, Google's tool is just phenomenal, so why don't we just use theirs? Okay, this is pretty impressive actually when you think about, because they're certainly probably no friends of each other. I'm going to look at my model, my job directory, so that I can look at the TensorBoard. I have A2B5. You can see A2B5 here. What I want to do is look at the images that are being generated. Okay, so these are a sampling, not all of them, but a sampling of the images that my generator is creating. Actually, it's both. Both the generator is creating and the discriminator is looking at. Okay, so you can also watch this as this proceeds. As the generator gets better, these images will get better, sharper, clearer, and more easily distinguished as a real digit, as a real number, versus just something that happens to have the same style but isn't a real number. Okay? So how far are we? Again, on the right side in digits, it will tell you how much time it's estimated to be remaining, when did things start, when did they end. Obviously, it's not 11:30 p.m. I think this must be UTC, maybe. I don't have that conversion in my head right now, what UTC is compared to ours. You can also look at the learning rate, a graph of the learning rate. It's a very typical thing to adjust the learning rate as you go through the training procedure. In other words, the idea is that you want the learning rate to be large enough to get you close to the minimum of the function to minimize the loss, but not too large to overshoot it, right? You could imagine a situation where you're finding, keep in mind that training is really just a massive curve fit, right? We're trying to find the minimum of this function, or at least, hopefully the global minimum, but at least some local minimum. And so what we're doing is this massive curve fit, and so as we get closer and closer to the minimum, we want to make smaller and smaller adjustments to the parameters of the function, okay? Because we don't want to overshoot the minimum, okay? So this is what this graph is showing you. It's showing you what the learning rate is, okay? You can see for the first while, it was 0.0002 and then dropped down here after some number of iterations. Okay, again, it's a very, very typical thing to adjust the learning rate and continue to make it smaller and smaller and smaller as you run more and more training. Because you would imagine, as the learning rate is large, at the beginning, we're just trying to roughly zoom in to the minimum of this function. And then as we get closer and closer to the true minimum, or what we think is the true minimum, we want to make smaller and smaller fine adjustments. Okay? So now we're 3/5 of the way through, 60%. A couple more minutes left on this training job. This thing says 4 minutes. You can also look at the data set. It says our image count is 60,000. Our image dimension is 28 by 28 by 1. These are grayscale images, so there's only one color channel. So they're actually really small, really simple images. Only 756 pixels. But again, it's pretty remarkable. Pixels are going in, right? And what's coming out is true or false. It's real or it's fake, right? The other side of the coin, a vector of size 100 is being input, and the output is actually an image of size 28 by 28. right? So the information we're giving the generator is a vector of size 100 or length 100, and from that latent vector, it's generating an image 7 times larger with 7 times more information. So that's pretty interesting. So let's see, let's look, notice again, our two losses right here are really converged onto each other. I think it says in the lab, if they're 0.69, if they're both 0.69, that's roughly the best we could do. And you can also see that our learning rate has reduced a little bit. Even though training is running, we are snapshotting this model, and so you can do something with the model even though it's not finished. You can say, okay, I've finished through epoch 3, I can do some visualization. Okay, and I might just do that while this thing is even going, after a quick look at TensorBoard. So some of these are really blurry, right? Some of these don't look like much at all. Let's reload this.
Question for you. How do you know that the generator and the discriminator have both reached like some equilibrium, like it's an error rate like this?
Yeah. So the question is, how do you know when they've reached a suitable equilibrium? When their losses are essentially the same, 50% on this graph when they converge essentially, right? If one is up, the other has to be down, right? They both can't be the same unless they're at essentially equilibrium, right? So as they diverge, something is bad. Either the discriminator is too good, or the generator is too bad, or the generator is way too good and is fooling the discriminator too much, right? So you want that convergence to happen. And in the notebook, it actually talks about ways you can help the generator, especially at the beginning. You can imagine that at the beginning of this thing, the generator is going to be really poor, right? We're just giving it a random z vector, and we're asking it to make a digit that looks kind of like the number 7. You know, if you imagine just in open imaging, you just had a child throw some paint on the thing, and what are the chances that's going to look like anything useful? Very low, right? So we really need to help the generator at the beginning do a little bit better. Okay, and there's some topics and techniques that we talk about here, because otherwise the discriminator is going to be much too good, and the generator is going to be much too poor at the beginning, because we start the thing out in a random configuration. Let's see if we're about done here. Close. Yeah.
When we check the loss functions over there, in the beginning, the generator loss isn't that far.
Right, we said it.
What it is right now. So.
It's very close, you're right. So there, like I said, in here there are some techniques to basically give it hints, kind of to help it out at the beginning, so that it's not so bad, number 1. Number 2, we're doing a really easy problem, right? Just a digit recognition. So it's, I won't say it's contrived, but it's meant to be easy so that we get the right answer in a short amount of lab time. Does that make sense?
Normally, that gap should be much larger, right? Initially.
Probably, yeah. Okay, so we are done. It took 12 minutes roughly. So what is the next thing?
Yeah, it's 2 seconds.
Okay, so on the model page, we're going to select the GAN inference method and then the MNIST class suite. This is actually kind of cool. Okay, so what we're asking the system to do is now sweep over the different classes. Remember, we have 10 classes? 10 classes of information. We have zeros, ones, twos, threes, fours, fives, all the way up to nines. Right, so we gave the neural networks some hints at the beginning where we said, okay, we know that we have some information. It's not just unsupervised data, but we can actually do a class sweep. So take a look. If you look from the top to the bottom, okay, and there's actually an animation up here in the upper left as well, you can see that we can create, we can interpolate between the z vectors of 0 and the z vectors of 1s in a particular style and sweep through the different classes. So if you look at the top, look at this row of, or column of zeros, it slowly morphs into a 1, okay? The same thing is true with this 1. If you look down, it morphs into a 2, okay? So what we're doing here is we're setting the style to be the same, okay? We're saying, okay, all digits are going to be the same, and we're going to sweep over the different classes, okay? So we're basically doing an interpolation over the classes. So it's kind of interesting, and you can actually see it up here in this animation as well. It's a pretty smooth animation where we're just sweeping over the different classes and noticing the transitions between, okay? And so at the top you see 0 through 9, and at the bottom you see 1 through 0, okay? So that's a sweep over the classes. The next thing I think we're going to do is a sweep over the styles. Yeah. So we're going to do the same thing. We're actually going to sweep over the styles. So now we're going to keep the numbers the same. I think we're going to leave those the same. Let's see. So instead of sweeping over the different classes of digits, and the classes again are 0 through 9, we're going to sweep over the different styles of digits that have been learned. Okay. Which one? Okay, notice that, you know what, these styles are not as different as the ones in your notebook, and I think the one in your notebook was actually trained with 60 epochs, and ours was only trained with 5. But that's okay, you can kind of see the difference subtly, but now we don't change the numbers, we change the styles that they are part of. So if you look from top to bottom, the style of the digits changes somewhat. Okay, so that's the first couple things that we can do with the digits piece of it. This talks about how we interpolated. The next thing we're going to do is look at training an encoder. In other words, let's figure out what this z vector is doing for us and try to gain some information there. So we're going to do the same thing. How many are we going to do here?
区块链不是听一下，区块链。今天的风特别大，今天应该有4、5个。区块链。3天，区块链开个3天。
Okay, so in the interest of time, I'm not going to actually go through this whole training procedure in front of you, but I kind of want to walk you through what the idea is. And the idea is that we're going to actually create an autoencoder, and then what we can do with that is give it an image of a 3, okay, or any image. And what's going to happen is the output is going to be a z vector corresponding to that 3. Okay, that's going to give you a particular style of image, and then you can take that z vector and input that into the generator and generate other styles, or generate the same style in other digits. Okay, and that's kind of what's happening here. We copy and paste that z vector, we click test, and you'll see a class sweep. And all of these digits, again, are of a particular style, and the style happens to be from the input that we gave it. Right, again, the z vector extracted out the particular style. It did not extract the number 3 per se, because we conditioned the scan. All right, but this extracted the particular style of 3, and then we can actually run this class sweep on all of the digits. Okay, so the second part of the lab has to do with the celebrity faces, and this is where it gets really interesting. So we've already trained the model here. Okay, it takes a lot longer than just the time that we have in this session to train this model to make it work properly. But you can see there are some papers there and some references. If you're curious about doing this, again, you could really reproduce this on your own with minimal problems. Okay, the celeb faces network, very similar, does not use conditioning, mainly because what would the class of the celebrity be? I suppose their name, right? But that's not going to be too helpful here. So these are the structures of the GANs. So what we're going to do is we're going to do the same thing here. We're going to find z vectors, and then we're going to actually manipulate those z vectors in such a fashion as to change these images, or create images of people. Right? People that don't exist, obviously, but we can change the features of their face. Okay? Okay, so what have we done here? We've basically generated the Z vector for various images, okay? So take a look at this woman on the top left. The left image is the input image. The right image is the result of generating the Z vector and then running it through the discriminator, or the generator, and then generating her image back. So basically, to go from left to right, you first run through the autoencoder, which remember is the discriminator plus the Z vector, and then you run through the generator to generate this person's image. All right, so we have Z vectors here. Okay, this is a vector of 100, and that's the result, okay, of generating this particular person's face. Okay, so what we did here is we actually took the pre-trained generator network, and we already have an attribute vector, okay? An attribute vector file, where we said, we picked out 40 different attributes of these models, okay? So now we actually get to do the funnest part of the whole lab. We get to decide what to do or how to create one of these people. Okay, so let's go bald, -1, black hair 1, male 1, smiling -1, wearing lipstick -1, and young let's go -5. Okay, so let me just show you one because you kind of get the idea. But basically, we're picking out attributes to either be expressed or not expressed. Okay, so we're generating this data. Okay, let's see what we came up with. Remember that these other ones we didn't even change, so they're just the same. But that looks pretty good, right? Male with dark hair, and so forth. So you can actually pick out, we don't have all 40 of the attributes here listed in the box. But basically, this is an opportunity for you to kind of play around, and it's kind of a fun way to do it, creating these fake people or whatever, but it's kind of a nice visual response to what's actually happening with the GAN, right? So we're changing attributes, that's changing the Z vector, and that's creating these images, okay? So this really brings us to the end of this lab. Again, my apologies for those of you, actually, no, let's do one more thing. Sorry, let me do one last thing. This is actually pretty cool.
Can I ask a question?
Yeah.
How do you figure out which entry of Z vector corresponds to which attribute?
Yeah.
By trial?
No. That was that function we showed you earlier where you say, okay, every image with black hair has a particular Z vector. I average all of those together. Every image that doesn't have black hair, I can get an average Z vector there, and you subtract the two. Okay? So the subtraction of those two is the Z vector which indicates black hair. Does that make sense?
Yeah.
Yeah.
It's not a single entry, it's
Many entries.
How do you go about determining a good size for that Z vector?
Yeah, excellent question. How do you go about determining a good size for that Z vector? Probably trial and error, which is like part of deep learning, unfortunately, is an art, right? So let me put it this way. There's no formula that I'm aware of that says use this for a Z vector, you know, the length of the Z vector. Like when we did that example earlier, it was color, it was shape, and what was the last one? Size? What was the size? The shapes, what was it? Oh, anyway, we chose 3, right? Because we felt like there was 3 things that were determining, right? So, in this particular case, they chose 100. I don't even know why they chose 100. And it may say in that paper what a good representation of the Z matrix is, or the Z vector, but I don't know the answer myself. Yeah, question?
Yeah, is that a parameter that you could train, or would that entail having to run multiple iterations of your model with different like sigmoid activations at the end?
No, you could certainly, could you train for it? I don't know if you could train to get the right value. It's possible. You could certainly, try a few numbers, say 10, 50, and 100, and a lot of this stuff doesn't take too long. But could you train to get the right value? I'm not sure about that. It's a good question. Okay, so the last thing I want to show you is actually really cool, where it kind of does the same thing that we did with the digits. It shows you progression from one type of face to another. So let me do this last one and then we'll be finished. Okay, so this one is going to do something similar to what we did with the digits, where we said, Okay, we're either sweeping over the styles or sweeping over the classes. This time we're going to sweep over or really convert one image to another image, slowly but surely. And so we started with a particular image, that will be the image that's in the upper left. And then over on the right-hand side, I believe, is the first sync, and the left-hand side is the second sync. So here it is. This is actually pretty cool. The animation is even there too as you watch. It's kind of freaky actually, as you watch the faces kind of morph into each other. And so here's the animation up in the upper left, and here on the left side is the static, moving over to this side and then down. And you can see slowly but surely the images change as well. Again, using the interpolation for moving the image to image. So, yeah, the last thing which I won't do actually is you can just plug in a picture and it will output the attributes, or some of the largest attributes anyway. Again, this is Jan LeCun, the example shown here. And you can see he's got, well, according to this thing, he has rosy cheeks, he's smiling, he has an oval face, a pointy nose, and high cheekbones. Okay? So that's what this particular network got out of the image of Jan LeCun. So this is actually a pretty cool place to stop. Again, for those of you that weren't able to run digits, my apologies for not making sure that the guest network had port 5000 open. I hope you still got something out of it. I think for those of you that registered, we're going to try to make sure that you guys get a credit to take one lab of your choice online as well, which will follow up. We may follow up with a survey too, asking you what you thought of the lab and so forth. Joe, do you have any more closing remarks you want to make about the ambassador program? Or?
So again, if you guys weren't here before, again, we have the University Ambassador Program. If you found this content interesting and you want to bring more labs like this to your academic community, present this at conferences, and other types of meetups and forums, again, please, I encourage you guys to go to nvidia.com/DLI, which will bring you to this page. If you click on University Program, you can apply there for the Ambassador Program. There's also a link there to the NVIDIA teaching kits. Again, if you're teaching courses in deep learning, accelerated computing, there's lots of other teaching resources there. And again, GTC, our technology conference, which is going to be held right up the road in San Jose in late March. If you guys are interested in attending for free, again, we're looking for TA volunteers at the DLI sessions at GTC. And again, if you haven't already, talk to Sarah. She was around here somewhere. Oh, there you are, right there. Come talk to Sarah and she'll get you signed up for that. So you guys can also send us an email if you decide later on. If you have any questions about anything, there's a contact us button there. So please get in touch with us.
All right.